right. So yeah, today I'm very excited to share with you guys our Hetu protocol. So forgive me, I just recently got a pretty bad cold, so my voice is a bit shaky. But hope everybody can hear me. Is it good? All good? Okay, cool. All right. So first, a quick introduction. So my name is Jialin Li. So I'm currently an assistant professor at the National University of Singapore, and also I'm representing at the Verifiable Labs to tell you more about our very recent Hetu protocol, where we try to generalize this generalized notion of distributed consistency for building large-scale decentralized applications. All right. So let me first start with, I guess all of you here are developers in the Web3 space. So you guys use or have been developing infrastructure or use large-scale peer-to-peer infrastructures. But so far, there are very limited number of options in terms of a kind of consistency you get or kind of security you get from this infrastructure. Right, so here I gave you sort of like a graphical illustration, the kind of a spectrum of consistency levels or the kind of trust you get from these infrastructures. So on the very left, far end of the spectrum, you get things like traditional TCP/IP stack or lib P2P or things like that, where you can build very fast networking, right? Communication between different peers in a peer-to-peer network. Right, but the problem is that you don't really get a lot of security or consistency from these infrastructures. Right, so you kind of get the bare minimum kind of security if you do end-to-end encryption. Right, so that gives you things like authentication, integrity of your messages, but you don't get much more than that. Right, so if you build distributed applications or decentralized applications which require a lot more security or consistency, instead, what you do is you choose the far right end of the spectrum, where you use probably a blockchain, use a permissioned BFT protocol, or you use any other form of infrastructure like layer 2 rollups, restaking, and other forms of infrastructure that gives you very, very strong security. Right? So you have a totally ordered set of blocks. Right? So everybody agrees on the order, so there's global consensus. Right? So security-wise, it's really good. So very strong consistency, but the problem is it's very slow. It doesn't really scale, right? So for many kind of applications, it's probably not ideal to use this infrastructure as well, right? But we can see that this is a spectrum, right? So you don't only have two endpoints. There's a lot of ground in the middle, right? So all these middle for security options and consistency options, they're currently not a lot of for you infrastructure-wise for you to use, right? But actually, we see that there are a lot of applications which can actually benefit from a more, slightly more relaxed level of consistencies or trust models to scale them, right? So here I just gave you a sense of example applications, but here definitely there are not a exhaustive list, right? So here things like social applications, right? Things like communication between different AI agents, right? Like games, social games. And more recent, like decentralized physical infrastructure, and so on and so forth. Right. So all these applications, right? One of the main properties that very interactive, right? So there are a lot of interactions between different parties in the network, a lot of communications going on, right? So putting them on chain is probably not the best option because of the scalability bottleneck. So even though you have more scalability options these days, but eventually because the cost and then there's still limited throughput and scalability, it's still not ideal for you to build these applications on top. On the other hand, these applications do require some level of security and trust and also consistency, right? So for example, if you're building social applications, you want to have some kind of consistency so that your followers, right, your tweets, right, so they follow your followers, right? So these are your metadata changes. There are some kind of consistency guarantees, right? So at this moment you either choose right the very infrastructure that they don't give you anything, or you choose like blockchains, so which are fairly limited in terms of scalability. Right? So in this talk, so we're going to introduce Hetu, which does provide this kind of middle ground where it offers a lot more kind of consistency and security options for you to build distributed or decentralized applications. Right, so Hetu is a peer-to-peer communication layer. Right, so compared to existing peer-to-peer infrastructures or communication infrastructure, it additionally provides this what we call the trusted event ordering naturally from this communication layer. Right? And then underlying it, we are leveraging a novel form of verifiable logical clock, which I'm going to elaborate in a few minutes. So the nice thing about Hetu is that it is very low cost and then very highly scalable. But also it provides the opportunity for distributed or decentralized application to build various consistency levels on top of it. And then, so it has really, really wide kind of applicability, right? So all the applications I just showed you will benefit from our communication stack. So let me just elaborate by starting from a little bit background, right? So when you build any kind of applications, distributed systems, right? So the order of events is a really important aspect. Right, so no matter what you do, you care about some kind of ordering, right? Either it's like between different blogs or between a social media post and then some other activities, right? So these are all events, and you care about the ordering. So how do you order events in a system, right? So the most traditional way. So for example, if you come to this ETHDenver event, where you look at all the events on the schedule, so you clearly mark. Right, what time is each event happening? Right, so that's the most traditional way of ordering events. Right, so my talk starts at 1:45, and then the previous talk starts at like 1 p.m. or 1:20 p.m. or something. Right, so by looking at the different timestamp, you can know exactly which event happened first. So, but the problem is that in a truly distributed or decentralized system, this kind of physical clock or commonly agreed physical clock is not present. So there are multiple reasons why you don't have that in a decentralized system. So first, from a theoretical perspective, if you guys have heard or learned about relativity, right? So in relativity, right? So different objects which have different relative motions, they actually don't have the same common clock. Right. So this phenomenon is called time dilation. So for example, here I show on the left is the International Space Station, right? So because it's moving with the relative motion with, for example, this is the location of ETHDenver, right? Because if there is relative motion, so the time actually disagree with each other, right? So they don't have the common time. So the other problem is that even if you don't have relative motion among different objects, because your clock's devices, they are not perfect, right? So they cannot track your physical time very accurately, right? So for example, depending on what kind of clock technology you use, if you use small atomic clocks, right, versus very sophisticated atomic clocks versus a simple clock you can find in your computer, like a crystal oscillator. So they have very different clock drifts, right? So it's very hard for you to have perfectly synchronized clocks among different parties, right? So if we can't have like a common agreed upon physical clock, what can we do to have to order events in a distributed system? So here we look back in the literature in distributed systems. So back in 1978, so a famous distributed system researcher, his name is Lamport, who later got the Turing Award for some of his work, including this. So he published a seminal work called Time Clocks and the Ordering of Events in a Distributed System, where he exactly talk about this problem. So if you don't have physical clock in the system, how can you order events? So he argued that the only trusted way of ordering events in a distributed system is to look at the logical ordering of different events. Or another way of saying it is called the causal ordering of events in a system. So what is causal event ordering in a system? So here I show if you have multiple processes in a distributed system, right? So they talk to each other through messaging, right? So you don't have a clock, so you don't know which event happened first, but you know for sure that if I send the message from process P to process Q, the sending of the event must happen before the receiving of the message. now establish a causal dependency between these events. And then you can use this if I receive a message and later send another event, I send another message, I know the sending of the next message causally depending on I received the previous message, right? Because the sending may causally depend on I actually received the previous message, right? And then you can do a transitive closure of these events. Then you get this, what they called a happened before relationship, which captured the causal or logical dependency between different events. So that you don't require any physical clock. And then that is the true ordering of the system that nobody can disagree with. Right? So that's a pretty cool and a pretty strong kind of event ordering property. And then Leslie Lamport argued that now we can develop a new kind of clock that doesn't depend on physical clock, but instead on a logical clock. This logical clock essentially tracks this causal dependency between different events. By looking at this logical clause, you can infer what's the causal dependency between different events. Right? So this paper and then the notion of logical clock on causal dependency have a lot of implication, a huge implication on the development of a lot of distributed and decentralized protocols to this date. So we are taking this protocol and this notion a step forward. So we are looking at how do we build logical clock in a decentralized environment, right? So in a peer-to-peer environment. One of the biggest challenges in this peer-to-peer environment is the presence of potentially malicious or adversaries users, right? So Byzantine nodes, or another way of saying it, right? So because traditional logical clock depends on all the participants in the system follow exactly the protocol of updating the logical clock, right? So if there are any Byzantine node in the system, it will break the entire notion of logical clock and the causal dependency guarantees, right? So what we do is we have done some recent research, and then we found we developed a new way, a new logical clock called verifiable logical clock that ensures that the logical clocks passed in the system can be verified by any third party, right? So that means nobody can create a false logical clock that breaks causal dependencies, right? And then, so I mean, I'm not going to have the time to give you all the technical background, but a high-level gist is that we leverage this new, novel application of zero-knowledge proof. So this is very recent development in the space. So this new technique is called incrementally verifiable computation, or IVC. That allows us to have multiple parties in the system by passing these messages, build a trusted logical clock with a verifiable proofs. Right? And by applying this novel kind of verifiable logical clock, we're able to build a lot of interesting applications and infrastructure on top of it. Here I just give you some quick examples that we recently developed, but you can certainly think of using this verifiable logical clock for a lot of more interesting applications. Right? So for example, we can use this verifiable logical clock to build decentralized mutual exclusion, or the other way of saying it is like a lock, right? A synchronization primitive between different participants in the system without centralized trust or centralized server for log services. Right? And you can build, as I hinted in the beginning of the talk, right? So there are a lot of applications that want something consistency levels that are not like strictly consistent, right? Not linearizable in a more technical sense, right? So here we are able to use this verifiable logical clock to build causally and eventually consistent data stores, and then things like virtual machines, right? So your virtual machine state doesn't need to be always synchronized across each other, but we guarantee either eventually synchronized, or if there's a causal dependency between the different updates, we make sure that everybody observe them in a causally consistent order, right? And then we can use this verifiable logical clock to build a shared sequencer, for example. Right here, we're able to use the partial ordering property of this verifiable logical clock to easily scale a shared sequencing layer. Right? And then, so far we have built so from this verifiable logical clock, we built a Hetu stack. So this Hetu stack, as I mentioned before, is a peer-to-peer communication layer. Right? So sorry that the picture might be a little bit blurry and small. So currently we can structure as three kind of layers. So the first layer is the underlying, the lowest layer. We have this messaging layer, where so the messaging layer creates the proof and then generate proofs and then verify for these logical clocks and verify this logical clock while generating messaging. And then this layer also build a traditional peer-to-peer communication layer, things like Kademlia, DHT, right? And then on top of it, we have a middle, or what they call the shim layer, where we build a sort of like a relay network, where there's a large-scale peer-to-peer network with a lot of participants messaging each other with the underlying the underlying verifiable logical clock in these each messages. And on top of it, expose a simple-to-use API to the application layer, where the application can use the logical clocks from the underlying layers to build their desired consistency levels and their applications. So that's the current Hetu protocol, Hetu stack. And then we are a very community-driven approach, right? So we developed a fairly interesting and pretty novel protocol called the Hetu improvement proposals. This is like the EIP system, right? Where everybody, not just our core development team, can propose different improvement on top of Hetu protocol or components of the Hetu protocol. Right. So here we gave you some, we roughly coarsely developed into 3 different layers. So the first layer is called HIP A layer. So this is the fundamental layers of the Hetu protocol. So here, we build the fundamental technology behind Hetu, things like logical clocks, the peer-to-peer network, and then the incrementally verifiable computation. Right. And then on top of it, there is the HIP B layer, where there is the middleware that people can build, things like the relay network I mentioned about, and also things like sequencers and then random number generators. And then there are many developers who care more about the upper level applications, and then they can propose things like messengers for social applications, decentralized games, or things like other kind of social applications on top of it. Right? So we open up this HIP system to all the developers in the system in the community. Right? Everybody can propose, right? And then once it's approved, they can be merged into the Hetu stack. Right? So currently we have a proof of concept. Right? So if you're interested, feel free to check out our GitHub page. Right? So currently we have a few of these components currently already built. Things like the verifiable logical clock, so the underlying peer-to-peer communication library. And then we also developed a few applications on top of it already as a demo. Right? Things like a social application called Z-Social, and then a random number generation. Right? So this is our proposed timeline for our Hetu stack and the Hetu protocol. So I don't know if you guys can read it, but we are currently roughly here. So where we develop our current proof of concept, POC. And then our goal is to have the test net sometime in the middle of this year, right? So which is here. And then later this year, and by the end of this year or early next year, where our plan is to roll out the mainnet of Hetu. So we welcome everybody to contribute, to talk to us, give us feedback. So many of our team members are here at ETHDenver. So if you are interested in our protocol or our stack, feel free to talk us. Akasha is here in this, I think somewhere here. That's me, and then I think Sean is also here, and then we have many other people here from the Hetu team. And then also follow us on Twitter, and then we welcome all your feedback. And then yeah, I think that's it. And thanks everybody.